In the previous section, we introduced the topics of eigenvalues and eigenvectors and how to find eigenvectors given an eigenvalue. In this section, we're going to explore how to find eigenvalues given the characteristic equation. So first, let's review what happened in the previous section. An eigenvalue lambda and an eigenvector x corresponding to lambda satisfy the equation ax equals lambda x. We said that if you take a vector x and you multiply it by a and you get a constant multiple of that vector out, that's what corresponds an eigenvector and value pair. We can rewrite this equation by subtracting lambda x on both sides and multiplying by the identity matrix to a minus lambda I x equals 0. And solving that equation, giving some lambda, we'll find our eigenvectors. Again, that's what we found in section 5.1. So we find eigenvectors by solving the above equation, but how do we find the eigenvalues? That's what we're going to go over in this section. We must have that x is non-zero. Note that if x equals 0, the above equation is always satisfied. It's a trivial solution, so therefore we don't want to consider it. So x is non-zero, and if that's the case, then that means that a minus lambda I x equals 0 has non-trivial solutions. And we talked last time that if that's the case, by the big theorem in chapter 2, the invertible matrix theorem, that if we have non-trivial solutions to a homogeneous system, that means that the coefficient matrix a minus lambda I is not invertible. And then we found with determinants that that means that the determinant of that matrix is equal to 0. We say that a minus lambda I is singular. And we must have that a minus lambda I is singular in order for eigenvalues and vectors to exist. So we need to solve the determinant of a minus lambda I equals 0, as that's what we must need to find our eigenvalues lambda. This equation, the determinant of a minus lambda I equals 0, is what we call the characteristic equation. Just the determinant of a minus lambda I is called the characteristic polynomial, and we'll see that that is a polynomial with variable lambda. So let's look at an example. This time we're going to find the eigenvalues of a matrix, and to do that we're going to find the characteristic equation and characteristic polynomial. So I'm going to take my matrix and I'm going to subtract lambda I as I am trying to find the determinant of a minus lambda I equals 0. So a minus lambda I, all that's going to change is the diagonal entries of a, and we're going to subtract lambda from all of them. That'll give us a 0 minus lambda, or minus lambda, and 5 minus lambda as my new diagonal entries. Then I need to find the determinant of that matrix, and note that the determinant of a 2 by 2 matrix will just be the diagonal entries, the main diagonal entries, multiplied together, and then subtract off the other diagonal. That's the determinant will give us that value. So solving my characteristic equation, that means I have negative lambda times 5 minus lambda plus 6 is equal to 0. And then we are going to factor. This is a polynomial set equal to 0, and we are always going to factor to get and to solve for lambda, our variable. So to do this, we can distribute the negative lambda across. That'll give us a lambda squared minus 5 lambda plus 6. And then that factors nicely into lambda minus 2, lambda minus 3 equals 0, which means that I have lambda equals 2 and lambda equals 3, which means that those are my eigenvalues of A. Those are the eigenvalues that satisfy the determinant of a minus lambda I equals 0. Those are the eigenvalues that will give, this will give a minus lambda I as a singular matrix, which means that if I try to find the eigenvectors, we'll have infinitely many solutions. We'll be able to find those eigenvectors. There won't just be the trivial solution. So when we're doing this finding eigenvalue process, we are going to be finding determinants of matrices. And let's recall that for 3 by 3 matrices or larger, we can compute the derivative, or the, not the derivative, the determinant by using a cofactor expansion. So let's find the eigenvalues of this matrix A. The solution, we're going to have A minus lambda I. So in this case, we're going to subtract lambda from all of the diagonal entries. And then to find the determinant, we're going to use a cofactor expansion. In this case, we're going to go a cofactor expansion across row 2. Why across row 2? Because that's where we're going to have the most zeros. So doing this cofactor expansion, I don't need to worry about the first and the third term. I just need to worry about the second. And if I delete the second row and second column, I'm left with the minor matrix. 1 minus lambda is on the diagonal, 1's on the other diagonal. And the power, or the coefficient negative 5 minus lambda, I need to multiply this by a negative 1. Second column, second row, 2 plus 2, that's just going to give me a positive 1. That's why it's not included in that calculation. So, now I have this as my determinant. I need to find the determinant of the 2 by 2 matrix, and note that I can do that by taking the entries on the main diagonal and subtracting off the entries of the other diagonal, giving me 1 minus lambda squared minus 1. And then I need to factor. I need to distribute across everything, get it into, in this case, a cubic, and then I need to factor. So I'm going to keep the negative 5 minus lambda, but I'm going to expand 1 minus lambda squared into 1 minus 2 lambda plus lambda squared, and I have a minus 1. The 1's cancel out, and I'm left with negative 5 minus lambda on the outside, negative 2 lambda plus lambda squared. And I can factor that by bringing a lambda out, and I have negative. I can bring a negative out of the negative 5 minus lambda. Negative 5 plus lambda, lambda, negative 2 plus lambda equals 0, which gives me my 3 eigenvalues, negative 5, 0, and 2. So to go over this example one more time, we need to find A minus lambda I, that's subtracting lambdas from the diagonal, find the determinant using the processes we looked at in chapter 3, in this case using a cofactor expansion, and then we're going to have to do some algebra on this polynomial to factor it as much as possible so that I can find the eigenvalues. So let's look at the invertible matrix theorem again, as we can add some things to this big theorem from before. So if A is an n by n matrix, the following are equivalent. And we call it the invertible matrix theorem because we're saying everything here is equivalent to saying that A is an invertible matrix. So all of these are a rehash of things before. It's a big review of everything we've seen in this course. But now we're going to add that if the number 0 is not an eigenvalue of A, the matrix is invertible. Note that if it is an eigenvalue, this means that AX is equal to 0 times X, which means that AX equals 0 has a non-trivial solution. And we can see that that is part D to that's equivalent to, if that's the case. Another way of saying this is now the determinant of A minus lambda I is not 0. And not just lambda, but this should be 0 I lambda, as this is just saying that the determinant of A is non-zero. We've seen that before, and in this case, this would correspond to 0 being an eigenvalue of the matrix. So let's look at another example here. Let's find the eigenvalues of A. In this case, we have a triangular matrix, an upper triangular matrix. We can see that because all of these entries above and the entries below are 0. And we said that if we have the a minus lambda I, that's subtracting minus lambda across the diagonals, if I have an upper triangular matrix, the determinant is just multiplying the entries of the diagonal. In this case, my characteristic equation is 3 minus lambda times 6 minus lambda times 2 minus lambda equals 0. So the eigenvalues are 3, 6, and 2. And we said in the previous section that if I have an upper triangular matrix, the main diagonal entries, 3, 6, and 2, are my eigenvalues. We can see maybe that's just true by this little proof of the determinant. Another concept of eigenvalues we're going to introduce is the multiplicity of the eigenvalue. The algebraic multiplicity is going to be the multiplicity as a root of the characteristic equation. It's how many times the factor corresponding to that eigenvalue shows up in the characteristic equation. And we'll see an example on the next page that has a multiplicity other than 1. In these cases, all of these have multiplicity 1, algebraic multiplicity 1, because the corresponding factors only show up once in the characteristic equation. We're also going to have a geometric multiplicity, but we're going to talk about that in a future section. The geometric multiplicity is going to be something different, and that's going to correspond to the size of the eigenspace. And we'll look at that later. I just want to make it clear that there are two multiplicities that we're going to be talking about with eigenvalues. The algebraic multiplicity comes straight from the characteristic equation. The geometric multiplicity is going to be talking about the eigenspace and the eigenvectors of the eigenvalue. So let's do one more example here. Find the characteristic polynomial and all eigenvalues, as well as their algebraic multiplicities when our matrix is A. And again, this is a lower triangular matrix. We can see that because we have zeros above the diagonal. We have this lower triangular matrix of entries. And if I want to find the determinant, I'm going to subtract lambda, and I'm going to multiply the diagonal entries, and this will give me the characteristic equation 2 minus lambda, 3 minus lambda, 3 minus lambda, negative 1 minus lambda equals 0, which means my eigenvalues are 2, 3, and negative 1. But in this case, the 3 has a multiplicity of 2. Again, we could rewrite this characteristic equation as 2 minus lambda to the first power times 3 minus lambda to the second power, negative 1 minus lambda to the first power equals 0. And these 1, 2, and 1, these are the algebraic multiplicities. So in this case, the 3 has multiplicity 2, the 2 and the negative 1 have multiplicity 1. Since this is a lower triangular matrix, we could have seen that from the very beginning. We have 2, 3, 3, and negative 1. The 3 shows up twice, so that's going to be a multiplicity 2. We should say that our eigenvalues we're going to have in our examples, there are 3 things that could happen. We could have real eigenvalues. We can have complex eigenvalues, and we can have repeated eigenvalues. We're not going to look at the complex case in this course, but we are going to have real eigenvalues, and those are repeated sometimes. And here is an example of a repeated eigenvalue, where the multiplicity is greater than 1. So then, introducing one last topic, we have the idea of similarity. we're going to say two matrices A and B are similar, A is similar to B, if there is an invertible matrix P such that its inverse, P inverse AP, is equal to B, or equivalently, A equals P, B, P inverse. Why is this equivalent? Because if I take this matrix and I multiply by P on the left on both sides, that'll give me P, P inverse AP equals PB. The P and P inverse cancel each other out. And then if I multiply by P inverse on the right, I'm left with A, P, P inverse equals P, B, P inverse, and the P and P inverse cancel out, and I'm left with A equals P, B, P inverse. So that's just saying they're the same thing. We're multiplying by a matrix and its inverse on either side of the other matrix. That means that those two matrices are similar, if we can do that. So why is similarity important to us when we're thinking about eigenvalues? This theorem says that if A and B are similar, then they have the same characteristic polynomial, and hence the same eigenvalues, as well as the same multiplicities of those eigenvalues. A lot of math boils down to taking some complex problem and making it easier, and this is what similarity is going to allow us to do. If we're trying to find the eigenvalues or look at the eigenvalues of some matrix, we can instead look at the eigenvalues of a similar matrix, where that similar matrix is easier to deal with. So for instance, if you have a generic matrix and it is similar to a upper triangular or lower triangular matrix, it's much easier to see the eigenvalues of the triangular matrix, so we can instead look at that if they're similar. That's the goal. We're going to go over that in the next section with something called diagonalization. So let's prove this theorem real quick. If B is equal to P inverse AP, then I want to show that the determinant of B minus lambda I, that's the characteristic polynomial of B, is equal to the determinant of A minus lambda I, that's the characteristic polynomial of A. And if those two things are the same, then they have the A and B have the same eigenvalues with the same multiplicities. So the algebra I'm going to do here is I'm going to rewrite B as P inverse AP, and I'm going to rewrite lambda I as lambda I times P inverse P. Why can I do that? Because I can rewrite this as lambda I times P inverse P, which is just lambda I. Remember, you can multiply anything by I. Maybe you can think instead, another way to think about this is, if I start with lambda I can rewrite I as P inverse P. And then, since I can multiply by I anywhere, or I can bring the lambda in front, I can write this as P inverse lambda times P, but I'm going to input an I in there instead. So I'm rewriting lambda I as P inverse lambda IP, and then I can factor out a P inverse on the left and a P on the right, and I'm left with A minus lambda I in the middle. Then using the multiplicity property of determinants, I can write this as the determinant of P inverse times the determinant of A minus lambda I times the determinant of P, and we can rewrite that as the determinant of P inverse P times the determinant of A minus lambda I, as these are just numbers, and I'm going to bring that determinant over there. And this is the determinant of I, so that's just 1, times the determinant of A minus lambda I. And I'm left with the determinant of A minus lambda I on the right. The P inverse and P cancel each other out in the right way when we're talking about determinants because I can do the multiplicity property of determinants, where I can't just do that with matrices themselves. So again, the purpose of similarity, we're going to see in the next section that I can think of a matrix that's hard to deal with, instead look at a matrix that's similar to it, that's going to be lower triangular or upper triangular or maybe just a diagonal matrix. That's going to be very easy to see the eigenvalues and eigenvectors of that matrix.